Hello, and welcome to a digital mathematics lecture for Salt Lake Community College. In this video, we're going to be going through the third section of Module 10, Normal Distribution. We're going to be talking about here the concept of z-scores. Up to this point, we've been working with the normal distribution and the empirical rule, trying to find the probability of values that are an exact amount of standard deviations away from the mean, either 1, 2, or 3 standard deviations away. However, the question is usually raised of, well, what if a number isn't exactly 1 standard deviation away? What if it's not exactly 2 standard deviations away? What if it's like 1.5 standard deviations away? Or 1.34 standard deviations away? Not a really nice number. Well, that becomes a little bit more complicated. That value, though, of the number of standard deviations away is going to be what we call a z-score. So a z-score is the number of standard deviations away a value is from the mean. So how many standard deviations away your given value is from the mean. That's going to be what we call a z-score. Now, in order to do that, to find a z-score, there is a defined formula for it. And I'm going to go through the logic of that formula. The z-score formula, so we just represent z. The first thing we want to do is just find how far away my number is from the mean. The value that we use, we consider x. So if I say my number x, I want to see how far away it is from the mean, and to do so, that's a simple subtraction. Just like how far away you are from an exit number, you just subtract your exit number from the one in question, and that tells you how far away you are for driving purposes. So this just finds the distance from your given value x to your mean mu. I then want to put that in terms of standard deviations. So in order to do that, what I'm going to do is divide that by the standard deviation itself. That way this finds that region here, the distance, how many standard deviations fit within that distance. And that's the entire formula, x minus mu over sigma. Do be careful if you do this in a calculator, though. A lot of calculators, a lot of scientific calculators specifically, may not have formatting for fractions, so you do need to be careful if you do this all at once. You would need to take your x value minus the mean in parentheses and then divide that by sigma. So you do need to be careful of that. If you don't do this, and if you just do x minus mu divided by sigma in your calculator, just putting in your numbers, this will not work because this will take mu divided by sigma and then subtract that value from x. So that doesn't do it. So just be careful when inputting into your calculator. Or you could just do x minus mu, enter, then take that number and divide by sigma. It's probably a little bit safer. All right, so the z-score will find how many standard deviations away it is. Now, and then we're going to ask, okay, now that we know how far away the value is, what do we use to find the area? Do we still do the empirical rule? The answer to that is no. We have a separate table that we're going to use to solve this, and I will bring up the table in just a moment. To show this, though, I'm going to do this example here. At a large department store, the average number of years of employment for a cashier is 8.7 years with a standard deviation of 2.1 years. So I have a mean of 8.7, just pulling out the data, and a standard deviation of 2.1. If an employee is picked at random, what is the probability that the employee has worked less than 6.6 years? So x is 6.6. Now, I'm going to address this problem just like I would with the empirical rule problems and just draw this picture. 8.7 is in the middle here, and I want to see where 6.6 is. Well, 6.6 is 1 standard deviation away. Well, if I go 1 standard deviation away, I go down 2.1. 8.7 minus 2.1 does give me a value of 6.6. And what we're trying to find is less than 6.6. We're trying to find this area down here. Notice that 6.6 is an exact amount of standard deviations away, so we can apply the empirical rule in this case. 1 standard deviation away in both directions represents 68%. And I just want one of these tails. So if I do 68 divided by 2, or sorry, not 68 divided by 2. If I do 100 minus 68, erase. If I do 100 minus 68, that gives me 32. And then if I cut that in half, that gives me the area in each of these tails. That gives me a clean 16%. All right. So I just wanted to do one as a reminder of the empirical rule and show that it's still applied, particularly because we're going to address these just as if they were empirical rule questions. So for the second one, again, we still have a mean of 8.7. We have a standard deviation of 2.1. This one asks, though, the employee has worked less than 12 years. So my x value in question here is 12. All right, well, 8.7 is in the middle here. And if I go standard deviations up to get to 12, if I go up 2.1, I get to 10.8. And if I go up another 2.1, I get to 12.9. Well, that number 12 is not one of those standard deviations away. It's somewhere between 1 and 2 standard deviations away. But the question is how many standard deviations away exactly. So that's where we're going to use a z-score to find this. Okay, trying to represent this. Okay, so 12 is maybe here as an idea. That might be where 12 is. So somewhere between 1 and 2 standard deviations, because it's between 10.8 and 12.9. Okay. Now, to solve this, we can find how many standard deviations away that is using the z-score formula. So z is equal to my number in question 12 minus the mean of 8.7 divided by the standard deviation of 2.1. So that's what I'm looking for here. So if we do that, if I do 12 minus 8.7, we get 3.3. Divide that by 2.1, we get an answer of approximately, I'll round to 2 decimal places here, 1.57 standard deviations. So that's how many standard deviations away it is. Note that this doesn't answer the question yet. What we're trying to find is the area all the way up to 12. I can use the empirical rule and say that it's like between 84 and 97.5%. That would be 1 and 2 standard deviations, including one of the tails. So I can use the empirical rule to find an approximate, but I want to find this area semi-exactly. In order to do that, we have a table to assist us, and I'm going to switch over to the table now. All right, so this is your z-score table. We have the table of standard normal probabilities for negative z-scores, and you have this picture of a normal distribution with the shaded region, and you have a huge data set of a bunch of numbers. Typically, there's also another page to this that has a table of standard normal probabilities for positive z-scores, and you see this shaded region with a bunch of values again. This table should be provided for you in the Module 10 learning resources, so make sure you have access to that. However, we want to talk about how to apply this. If you remember, the z-score that we had was 1.57. Specifically, it was a positive 1.57. This table here will represent your z-score using the x and y axes. So this x-axis and this y-axis. And that's how we're going to find the probability. We're going to find this z-score in question, and then the other number here, the decimal in the middle, will represent the probability of that. Specifically, if you notice the graph presented here, it will always give me the probability below some number. so the probability below some z-score. Thankfully, in my previous question, I wanted to find the probability was below 12, or in this case, less than 1.5 standard deviations. So we're fine with that. Now, how to use this table exactly? Well, I'll scroll down a little bit. Well, what I want to do is find the z-score. The column here will be where you start. The column will represent the whole number and then the first digit after the decimal. So you see 0, 0.0, 0, 0.1, 0, 0.2, 0, 0.3, 0, 0.4, 0, 0.5, etc. I want 1.5. So if I scroll down, I see 1.5 right there. The second digit after the decimal will be your columns here. So 0.00, 0.01, 0.02. I want the third decimal or second decimal to be a 7. So that means I want to go over until I see 0.07. Then to find the probability, I scroll down this way and I scroll over this way until I find the cross region here, which is right there, 0.9418. So 0.9418. That's the number that I'm looking for from 1.57. That would be my area for this question there, 0.9418. So if I go back to the Module 10 notes, I can then say over here that the probability x is less than 12 is 0.9418, or in percentage, 94.18%. And that would be it. That is how we're going to apply the z-score table. One important point to keep in mind, though, with the z-score table is that it's always the probability below some z-score. However, what we can use is the concept of complements to find the area above it. So if we find the area below is maybe 70%, that means the area above it is 30%. Nice. I talk about that because this next question is going to require that knowledge. The employee has worked for more than 7 years. All right, so again, my mean is 8.7, standard deviation is 2.1, x is now 7. Well, on my graph, 8.7 is here. If I go down 1 standard deviation, I get to 6.6, right? Yeah. I get down to 6.6. And 7 is somewhere in the middle of that. So 7 is maybe like here or so. That might be where 7 is. And what we're trying to find is the area more than 7. So more than 7 is what we're looking for. Well, first what we need to find is how many standard deviations away that is. On my graph, it looks like it's less than 1 standard deviation down. So if I do my z-score formula, if I take 7, my value, subtract away 8.7, and divide by 2.1, so 7 minus 8.7 divided by 2.1, we get negative 0.81 approximately. So negative 0.81 approximately. Note that the value is negative. That does not mean that it is wrong. That just means it is that many standard deviations below the mean. So negative just means it's below, positive means it's above. That's all negative and positive imply in this case, just the direction. All right, well, we're still trying to find this value. We know how many standard deviations away it is, but we don't know the area yet or the probability. To do so, yet again, we're going to keep in mind our z-score of negative 0.81. I think I said 1.8 before, negative 0.81. And then we're going to go to our z-score table. The one we just worked with was a z-score table for positive z-scores. we want negative. So I'm going to scroll up to find the negative z-scores. That's what we're looking for. Furthermore, keep in mind that the area that this table will give me is the area below the z-score. We want the area above. So that means we want to take the area that we find from this table and subtract it from 1 to find the complement. All right, so keep in mind our z-score here was negative 0.81. So that means our column that we start with, the z, should be looking for negative 0.8. So that means we got to scroll down until we find negative 0.8, which is right there. And that gives us the first decimal point. We want then the second decimal point to be a 1. So that means we want this column right here. That together would make negative 0.81. All right. Now then, if I scroll down this, so if I go from 0.01 and I scroll all the way down, and then I go over from negative 0.8, I get this value right here, 0.2090. So that's going to be my answer there, 0.2090. So 0.2090, or 20.9%. All right. Now, if you're wondering where that table comes from, it's the same thing I talked about with the empirical rule. It's all coming from calculus. It's all talking about the area under a curve from one region to another. It's a very simple operation in calculus. However, we don't have those that math here, so we can't really talk about it too much. It's already been made for us, thankfully. All right, last question of this example, and then I have a couple more. The employee has worked between 6 and 12 years. All right, so this one's going to be a little bit tricky. So mu is 8.7, standard deviation of 2.1, and I have two x values here. I have x1 is 6, I have x2 is 12. Well, 8.7 is there in the middle, and I know 6, if I go one standard deviation, that's 6.6. And then 6 is not quite 2 standard deviations. It's going to be somewhere around here. So that's where 6 is. 12, we actually indicated before. We indicated in the second example there. So one standard deviation was 10.8. And then 12 was about another half standard deviations up there. So 12. And we want to find the area here. All right. So this one's going to be a little tricky. The reason is because the z-score table only really gives us the area below something. It doesn't find area between given values. However, there is a nice way of dealing with this. If I draw a picture here, what we can do is find the area from 12 and down, which would be this region here. I could find that region, and then what I can do is subtract away the region from 6 and down. If I do that, that will result in this graph here, because it will find all the area from 12 all the way down until we hit 6, because this tail has been removed. So that's the way we're going to find it. We're going to find one probability for 12 down and then for 6 down and subtract those two. One of those we already found. For 12, we found that earlier. We found that area was 0.9418. Now we just need to find the area for 6 and down. Well, to do that, we could do a quick z-score. The z-score for 6 would be 6 minus 8.7 divided by 2.1. Notice in all these cases, the only number I'm iterating on is this first value, x. So if we do 6 minus 8.7 and divide that by 2.1, we get negative 0.129 approximately, or negative 1.29. And we can use that to find the probability for 6 and below. So I'm going to go back to my z-score table. And we want negative 1.29. So I'm going to erase all this. All right. All that is gone. All right. So we have our new z-score of negative 1.29. Notice that it is negative, so we're still in the negative z-score region. If I go to negative 1.2, so I scroll down to negative 1.2, which is here, and then I went over to 9 for the second decimal point, I can then scroll all the way over and all the way down to find my area right there, 0.985. All right, so we have still on highlighter. 0.0985. If we subtract those two values, so 0.9418 minus 0.0985, we get an area of 0.8433. Or 84.33%. All right, so those are a little bit tricky because it involves two different values. However, in all of those circumstances where you have between two values and you're using the z-score table, you always just need to subtract the larger one from the smaller one. That's all you ever really need to do. So it shouldn't really be too complex. Okay, I have a few smaller examples of some more applicable ones and ones that ask other specific kinds of questions. Example 6. In a normal distribution, what z-score separates the lowest 30% from the rest of the distribution? And also keep in mind, if you want to try this and example 7, go ahead and pause the video and see how you do. So we want what z-score separates the lowest 30% from the rest of the distribution? That's kind of a weird question. So that means that we want a z-score such that the lowest 30%, so this area here represents 30% of the data, separates out from the rest of the distribution. And we want to find what z-score this is. Well, what that means is that we need to use that z-score table, but we need to work with it in a little bit of a different way. Do keep in mind that the z-score for 30% would have to be below the mean because the mean below would be 50%. So the lowest 30% has to be somewhere down here. So the z-score is going to end up being negative. So we know that z is negative. We know the z-score has to be negative because it's below the mean. It has to be. But we don't really know too much else from that. We need to go into the z-score table to try to figure this out. We need to figure it out in a little bit of a different way. Okay. Let me erase these things. Okay. So we're on the negative z-score table here. And again, remember that this table will give you the area below something, which is exactly what we want. We want the area below something to be 30%. However, we don't have a z-score to find the area. We have the area to find a z-score. So that means what we need to do is that we need to work from the inside of this table out and find the z-score that corresponds to 30%, or approximately that. All right, well, to do so, what I'm going to do is look around the table until I see 30%. And the numbers do increase and decrease accordingly as you go row by row. So for example, 0.1151, 0.1131, 0.1112, 0.1093, I'm getting smaller and smaller as I go this way. And if I do columns, 0.1131, 0.1335, 0.1562, I'm getting larger as I go this way. So if I'm looking for bigger numbers, I'm basically going down this direction. If I'm looking for smaller numbers, I'm going that way. But it's basically just a search. So look around until you find 0.30 or something really close to that. In this case, we're not going to find 0.30 exactly, but we are going to find something kind of close. If I'm looking around here, I see 0.2743, 0.3085, so it's going to be somewhere in between those. 0.2912, 0.2946, 0.2981, 0.3015. So those are the two values where I find 0.30, or 0.30 will be somewhere in the middle of those. So that's what I'm going to be looking for. I'm going to be looking for values in the curve that look like 0.30, or they're approximately pretty close to that. Now, depending on the question, it can be presented as either of these because they're both about equidistant. One is a little bit closer than the other. Or what you can do is split the difference. Find the number that would be right in the middle here. Well, the first one, 0.3015, that would be negative 0.5, and if I go up, 2. So this first number would be negative 0.52. The second number would likewise be negative 0.5, and if I go up to the top, I would see a second decimal point of 3. That would be those z-scores if I'm creating the z-scores in the opposite way that we did before. Instead of taking the z-score and finding the area, we're taking the area and finding the z-scores by finding what row and column it corresponds to. In the middle of those, so between negative 0.52 and 0.53, I can say that the z-score is approximately negative 0.525. So it's like between negative 0.52 and negative 0.53. So I will say the number that's right in the middle of those, or the average of them, negative 0.525. That's what I would say is the answer. So that would be my answer for my z-score. How many standard deviations away that value is. So this is showing how you can use the z-score table in a little bit of a different way by using the area and going outward. Now this one didn't really have any applicable cases to it, so that's what I'm going to do in the next couple examples, is do a couple of these where we find the z-score but do it with an applicable circumstance. Example 7. In order to be accepted into a veterinary science program, applicants must score within the top 4% of the pre-vet screening test. Given this test has a mean of 1400, so mu is 1400, and a standard deviation of 200, what is the lowest possible score a student needs to qualify for acceptance in the veterinary science program? All right, so on my graph, I have 1400 here, and what we're trying to find is the top 4%. That means we're trying to find this region up here such that this tail on the right side corresponds to 4%. That'd be the top 4% of individuals. And we're trying to find what this number is. Well, to do so, I'm going to need to find that z-score and then use that z-score, or I'm going to need to find the z-score and then use that z-score to find the given x value. Because we know that the z-score formula is z equals x minus mu over sigma. If I have mu, if I have sigma, and I can find the z-score by doing the process we just talked about, that means I can do a little bit of math to find x, which is what we're going to do. Now, keep in mind, it does say the lowest possible score. That means that anybody in this region, this 4% region, would be within the veterinary science program, the lowest possible score would be this boundary right there. So we're trying to find that bound. Okay, so if 4% is above, that likewise means that below this is 96%, is below that. And that's what we're going to need to use with the Z-score table, because remember the table always wants the area below something. I also note that the number is above 1400, so I should be looking for the positive Z-score region. Okay, so we're looking for something up here, and what we're trying to find is 96%. If I even look at this graph here and think about that, what I'm trying to find is this white region is 4%, which complementary means the shade region is 96. 100 minus 4. So what I'm looking for here is I'm going to scroll around here, and I'm going to be looking for 96%. So I see a lot of 96s. I see 96.16, 96.08, 95.99. That's really close. So that's probably the one I'm going to use. That's just 0.0001 away. So I'm not even going to split the difference here. I'm just going to use that value because it's just so close. It's just 0.0001 off. So that means that going out to create my z-score, I have 1.75, it looks like, yeah. So 1.7 the first two digits, and then 5 is the third digit. So that's what I'm looking for. So that means that I find that the z-score is 1.75, approximately. If I use that in my formula, 1.75 as my z-score, I can try to solve for x by plugging in everything else. 1400 for the mean, and a standard deviation of 200. All right, so we need to do a little bit of algebra. I'm going to multiply both sides here by 200. If I do 1.75 times 200, I will get an answer of 350. And that equals x minus 1400. So that's how I get rid of that division. And then if I add 1400, I should get an x value of 1750. So 1750 is the lowest possible score a student can get to qualify for acceptance to this program. All right. So that one's not too bad. A lot of these questions where you do have to find the percentages, it should be a very easily defined z-score instead of like splitting the difference, but sometimes you can. Last question here. The manufacturers of a certain widget need to ensure that the widget is exactly 12 inches long. Any widget made that is more than 0.1 inches off is considered unusable for its intended purpose. If the machine used to construct the widget follows a normal distribution, so it's normal, with a mean of 12, so mean of 12 and a standard deviation of 0.05, approximately 90% of widgets are between what two lengths? All right, so we have a mean of 12 here, and we want 90% are between what two lengths? So that means that we want, if I just try to arbitrarily put values here, I want a value down here and a value up here such that this represents 90% of the data. So the middle 90%. All right, that means I'm looking for two different z-scores. I'm going to be, or values really, looking for a value down here below 12 and a value up here above 12. Well, to do so, like before, we really want the area below something. So this first z-score, I'll say z1, has 5% below it via the symmetric property. If 90% is in the middle, that means 5% are in each of the tails. 100 minus 90 is 10 divided by 2. And that means 5% is up here. And the second z-score has 95% below it. So that's what I'm going to use to find each of these. 5% below and 95% below. And then we're going to solve for each of those. So I'll put both these formulas over here. So I'll say z1 equals x1 minus mu over sigma. And we're also going to find the second z-score as well to find the second value. We're going to need to find both of these. All right, so keep in mind 5% below and 95% below. All right, first 5% below. Well, 5% below means that it's below the mean, so it has a negative z-score, so we're looking for somewhere over here. And we're going to scroll down until we find somewhere around 0.05. That'd be 5%. And what I find here are these two values, 0.0505 and 0.0495. Directly in the middle of those is 0.05. If I add those two together, divide by 2, I get 0.05. Directly cuts them in half. So then what I'd be looking for, if I scroll over, I'm looking for a negative 1.6. And then between 0.4 or 0.04 and 0.05. So that means I'm looking for 1.645. That would cut those two right in the middle. Because this would be 1.64, this would be 1.65, and directly in the middle of each of those is negative 1.645. All right, so we found our first one. I'll go over back to our notes and put that value in. So for z sub 1, we have negative 1.645. Now let's check our z-score table for the other one. The other one had 95% below, so we're looking for the positive region over here. So again, erase these. We're looking for 95%, and if we scroll through, we find 94.95 and 95.05. Yet again, 95% cuts those directly in half. Now, if I try to find the z-score, I go over, and I go up each of these. So I find 1.6 and between 0.04 and 0.05. That means I'm looking at 1.645 again, except this case I'm looking at the positive version of that. Now, that may seem kind of weird to you, that one was just the positive version of the other one. However, it's basically trying to think about something like the empirical rule and symmetry. If there's 5% below one number and 5% above another number, then that means they should be the same distance away. So this z-score is the same distance as this z-score. This one just has a positive 1.645 here. All right, so that's what we're going to use. We found each of our z-scores, and we can find what the values would be corresponding to that. So we have x1 minus 12 divided by 0.05 in each of these, x2 minus 12 over 0.05. We can find what each of these values are. First, on both of them, I'm going to multiply by 0.05, so 1.645 times 0.05. I get 0.08225. Negative for this one. And this one over here, I get positive 0.08225. Whoa. 0.08225. We found each of those. And then for each, I am then going to add 12 to get x by itself. So if I add 12 to the negative version of this, 0.8225, I get that x1 is 11.91775. And then I get x2 is 12.08225. So those would be my two values. Approximately 90% of the widgets are between that many inches long and this many inches long. Via the question, they said that it's fine if it's within 0.1 inches, but if it's more than that, it's bad. And both of these values are within 0.1 inches, so they both seem okay. They're both usable for their intended purpose. But that wasn't really part of the question. All right, so that was probably the most complex one because you had to find two different values. But if it does split the difference like that, one z-score should be just the positive and negative version of the other one. So not too bad. But overall, that shows you how to apply z-scores, how to apply finding an unexact number of standard deviations away from the mean. With that said, you should be able to complete all the homework for Module 10 at this point, as well as the quiz, so go ahead and try your hand at both of those. With that in mind, I hope that you have a wonderful day.